Yeah. Okay. I can see someone. Good. Okay. So we want to start doing functional analysis, and so for that, first we want to define what is called a Banach space, and before that we want to define what is called a non-linear space. So we will fix we will fix a vector space. So all of you know what is a vector space. You must have studied in linear algebra courses or algebra courses. So this is where the class starts. Okay. X be a vector space, linear space. It's also called linear space or a vector space if you want. Okay. Linear space means if you take 2 points, then there should be a concept of line joining there, and that should also be there. Okay. So this is a linear space. We will always consider linear spaces over complex numbers mostly, unless otherwise it is stated, or real line. Okay, real field we will not consider mostly. I mean, we will consider basically complex. You can consider any field, but for our purposes, we will consider complex field. Okay. So sometimes there are a few things which doesn't hold for real because that's not algebraically closed. So we will consider complex field. Okay. So this is the then the definition. So when we have a linear space like that, then a function. So this is what is called a norm. Norm is a function from x to 0 infinity. I mean, this is, of course, we have come out of measure theory, so we are not.
So by linear space you mean vector space?
Huh? Say it again.
By linear space you mean vector space?
Yeah, linear space is also called vector space. Okay. It is just, sometime some people may say normed linear space or normed vector space. Whatever comes in my mind, I will say, okay. So both are same. Linear space or vector space are same. Okay. So some people call it linear manifold or something. So it's I will not use that. Okay. Okay. So a function, it's a function defined on the vector space and takes values in positive real line. It's a real number. It does not take the value infinity. Is a norm. Is said to be a norm. Is a norm. If first one, we have already said it's greater than or equal to 0. So norm x equal to 0 implies x equal to 0. Okay, for all x in x. Okay. So this is what is called faithfulness. So this, I mean, every x which is not equal, so it's a vector space. So 0 is an element, and if you have any non-zero vector, that has a very strictly positive norm. That's all. Okay, that has a strictly positive norm. The second one, if you can, it's a vector space, so you can multiply any vector by a scalar, where scalar is from the complex field. Okay, complex or real, whatever. I have started doing this. So if you have, so alpha times x, norm of alpha times x equal to mod alpha. This is just a number, so I take mod alpha. This is scalar, mod alpha times norm x. For all alpha in C and x in x. Okay. Then the third one, which is what is called triangle inequality. Okay. Which you must be knowing already for modulus. It's the same thing. Norm is norm. Okay, so any function, any positive valued function satisfying these three properties, this is what is called positivity. This is positivity or faithfulness. This is just, I mean, the scalar multiplication. What happens under scalar multiplication? This is triangle inequality. Anything which satisfies these three properties is called a norm. And any vector space together with this norm is called a normed linear space or normed vector space, whatever. Okay? Normed linear space. So if X is a normed linear space, if X is a normed linear space, okay, NLS means non-linear space, then you can define d of xy equal to norm of x minus y. This you must be knowing already. I mean, you must have seen it in metric spaces or something. This is a well-known metric. Then this is a metric. It's easy to see this is a metric. Is a metric. Okay. So it's clear, positivity will follow for positivity of the metric. I mean, d of xy equals 0 if and only if x equal to y will follow from the positivity of this. And triangle inequality symmetric is clear because it's a vector space. So addition is x plus y is same as x minus x. I mean, mod of norm of x minus y is same as norm of y minus x. That's because you can multiply by the scalar minus 1 or 1. I mean, it's clear. And triangle inequality will follow from that triangle inequality. So it's an easy exercise to show that this is a metric. So this gives a metric. So this is a metric space. So since this is a metric space, then we say definition. A Banach space is nothing but X is a Banach space if complete. I will not write this D. I mean, when I say something converges with respect to this norm, it converges with respect to that metric. It's complete with respect to this norm. Okay, that means it's complete with respect to that metric. So if every quotient sequence in that has a limit, is convergent, has a limit in this vector space, then we say it's a Banach space. Okay. So before getting into it, let us see some properties of this norm. So these are all very simple exercise, but I will orally give you the proof. Okay. First one is the norm is a continuous function. Norm is continuous. Okay, if you have any norm that's continuous, we may use it. That means if you have, so this is a metric space, we can use sequences. So if xn converges to x, then norm xn converges to norm x. Okay, that's what it means. Okay, and this should, yeah, someone is saying something. Okay, so please mute it.
কোথায় ইয়ে থেকে ঢুকেছিল না গেটে
মিউট কর
এরা বলেছিল ভ্যানে গেট ঢুকেছিল
প্লিজ মিউট
ভ্যানে ঢুকেছিল সৌম্যদেব বলেছিল ভ্যানে গেট ঢুকেছিল
He's having his headphone there.
আমি পুরীতে চালাই গাড়ি আমার জোরে চালাতে নিজেরই ভয় লাগে পিছনে বসলেও ভয় লাগে আমার স্পিডে ভয় লাগে
Someone tell him in Bengali that ask him to mute, please.
এটা
mute kar.
Okay, so if so what I'm saying, so norm is a continuous function. So this follows, you have to say that what does it mean to xn converges to x. So norm has this property. First, the property is we have triangle inequality. From the triangle inequality, it follows that norm x minus norm y is less than or equal to, you take the mod also. This is, I mean, well known through modulus. The same trick is less than or equal to norm x minus y. Okay, this you can see because x equal to x plus y minus y. So you can write this as, I mean, it's very easy. You can write it. So from this it follows that if xn norm xn minus x, norm xn minus norm x, if you take this is less than or equal to norm xn minus x. So if something converts, norm xn converges to x means this goes to 0, this side goes to 0, then this will also go to 0. So norm is continuous. Okay. The second, so this is norm is continuous. That's clear, I believe. So that is the first observation. Then the plus the addition scalar thing, scalar multiplication is continuous. So addition, there's an addition. These are the only operations in the vector space. So addition and scalar multiplication are continuous. Okay, so that should also be clear because if you want to, I mean, so if you want to prove first addition is continuous, so xn converges to x, yn converges to y, then you want xn plus yn converges to, so you just have the xn plus yn minus x plus y. This should go to 0. That's all. But this is less than or equal to norm xn minus x by triangle inequality norm yn minus y. Okay, so it follows that addition is continuous. Similarly, if alpha n converges to alpha scalars, alpha n scalars, okay, alpha is in scalar, and xn converges to x, then alpha n xn minus alpha x, if you take this is less than or equal to, this is clear, mod alpha n times norm xn minus x plus alpha n, this is mod alpha n minus alpha times norm x. You can write it like this. Okay, and this is a converging sequence, so this should be bounded. So this is less than supremum over n of mod phi n. This is just a number, and xn minus x plus this. This is also a number times mod alpha n minus alpha. So due to those conversions, this will also converge. So because of these inequalities, scalar multiplication is continuous and addition is continuous in this vector space. Okay. So that's what we have seen. So now we see some examples. Okay. All these algebraic operations are continuous. It's always important to verify these things. See, so let me say, what is this functional analysis? Functional analysis. So however this started, I mean, this functional analysis as a subject, it started as something as, instead of considering some function, a particular function, the idea is to consider a space of functions. Then you can prove theorems about that. So that is why, I mean, it is basically to say most of this mathematics arises from problems in physics. Okay, even though mathematics is very abstract or something, but let's say there is a root in physics. Okay, so one of the important thing is to solve some partial differential equations or something. So then you have to consider the solution space or something. So because of that, then the solution space form a nice vector spaces, and you can, so when it is, so then that is how the whole mathematics develops. So when we want to deal with some problem, then we make it an abstract mathematics question. Then we forget about the physics. Then we do the mathematics. So that is how functional analysis more or less started. And functional analysis is basic. So there is nothing about we will not see any function here. But this is about function spaces. So you are making statements about collection of function spaces, as we will see. So that is why these examples are coming. And so no, one important thing about functional analysis is, I mean, what makes it beautiful is, it is an interplay between, I mean, this is the structure given to the object they are considering is Banach space, linear operators, and all those things. These are objects which has both an algebraic structure and a topological structure, right? I mean, it has an algebraic structure. The norm gives a topology, and it has an algebraic structure. So we give both the structure. So whenever we give both the structures, we have to verify that those structures are compatible. For example, if you have a ring or something, then we will say you have an addition operation, you have a multiplication operation. So then there should be a compatibility between them. That is what is given by what is called the distributive property, for example. Okay, when you have addition and multiplication, then you need distributive property. Similarly, when you have a continuity, when you have a norm, then you can talk about continuous. So they have an algebraic operation. So you have to first verify that these algebraic operations are continuous. Okay, then that's why then only there is a compatibility between these structures. Okay, there's an algebraic structure, scalar product and addition and all those things, and there is a topological structure. These two structure are compatible is what we have verified. Okay, addition and multiplication, these are all continuous. Okay, now let us see some examples. So the basic examples, as you know, is all Cn or C or whatever, Rn. This is Cn is over C, Rn is over R. So you know the usual metric, but we are going to consider something more than that. So I mean, you can consider any of the usual metric, usual norm you can consider, which is norm X. I mean,
Sir, are you giving examples of Banach spaces or like just norm vector spaces?
Banach spaces. We will see. I mean, whether if it is not complete, it's not a Banach space. Okay, we will give norm linear.
I believe it's not complete.
What?
Nothing, sir.
So these are all certainly complete. These are all finite dimensional, so it's all automatically complete. Okay, there is no need. I mean, these are all complete. So you can put any norm on this. We will see that all norms are equivalent. So you can put any norm, but we can consider this norm. Norm x1 up to xn equal to summation mod xi square whole power half. Or you can say this is norm 2. You can call this norm 2. Or you can talk about x1 up to xn p, where p is greater than or equal to 1, less than infinity. That is equal to summation mod xi power p whole power 1 by p. This is LP norm. You can talk about this. Okay. Or you can infinity equal to supremum. So this is just a maximum. I mean, whenever it's maximum, we have to say maximum over I of mod xi. There are only finitely many. So you can check that these things are norm. But I want to give an excess. I want someone to present the following. So if you have a measure space, so this is the presentation. Whoever wants to present, you, I mean, either write it in the chat now or you will write a mail after this class. Okay. So this is what you want. I want you to prove. This is the presentation. So X something mu be a measure space. Okay. We have already seen in the last presentation about this LV spaces and other things, but I want you to prove that it's complete. That's all. Then define. So then you call this LP tilde equal to all those f function from x to c such that integral mod f power p is smaller than finite. Okay. Then you consider this space, this LP equal to LP tilde, or maybe I will put a p on the top also, divided by
Which
this.
space did you ask to prove completeness?
You're saying something? Yes?
Which space did you ask to prove completeness about?
I'm going to say, I haven't finished these LP spaces.
Okay.
Right? So where this equivalence classes f is equivalent to g if f of x equal to g of x almost everywhere. Okay. You consider this function space where all those functions from the measure, this measure space where the measure is defined from x to c such that f power p is integrable. Okay, over this is integrable with respect to this mu. Then you quotient that space with respect to this f of x equal to g of x. Okay, then define norm fp equal to integral mod fp. This is finite. Okay, over this x d mu whole power 1 by p. Okay. And if you use the Minkowski inequality and Holder's inequalities, which we have already proved, then this will be a norm. This will satisfy triangle property. Because I've already quotiented it out, you already know that positivity is certainly satisfied and the integration is linear. So it's a norm. It's easy to verify it's a norm. And using the Holder's inequality, which is already proved by Arca, it's clearly a norm. And you have to prove that it's complete. Okay. LP or LP, whatever. I can say P, I can put P in the top or bottom. Okay. LP is complete with respect to this norm. Okay. This is one thing. This is for P less than infinity, greater than or equal to 1. Okay. And this is, and also for infinity. So L infinity is defined to be something like this. All those F from X to C, such that it's bounded, but it's what is called essentially bounded. This is the mu of.
But if we have an analogous of this triangle inequality for LP spaces or P is less than 1 as well, right?
Yeah, but that's not a norm. That's only a metric space. You will not be able to prove norm.
What goes wrong with that? Okay.
Yeah. That's a metric space. That's okay, but it's usually we will be dealing with this p greater than or equal to 1, so that you have the other q 1 by p plus 1 by q is that will also be greater than or equal to 1. So the q which satisfies the conjugate of this, which you defined in the last class, so that will also be greater than or equal to 1. So the LP LQ, there is a correspondence that we will talk about it later. So the L infinity is all those F such that you take this mu of mod F greater than M it's essentially bounded. So that is just mod F mod F of X. How do you say that? Mod of F of X is less than or equal to, there exists a M such that mod X is less than, mod F of X is less than or equal to M almost everywhere. Okay. This is L infinity. Then you define norm of F infinity for F in L infinity to be infimum of all those m such that mu of mod f of x greater than m equal to 0. Okay. So here you have to, one has to prove that it's also a norm, which is not very difficult. Okay. Then L infinity is a Banach space. Okay. Is also part of this presentation. This is not very difficult. Prove that LP is complete. LP is a Banach space and L infinity is a Banach space. Okay. And I will give one more thing for the presentation. That is, you take any set, S is any set. Okay. Then consider this B of S equal to all those. I mean, the proof is same. That's why the proof is very similar to this L infinity. If you have a measure, then then it's the same thing. So F from S to complex numbers, and F is bounded. Okay. Then you can define for F in B of S, define norm F infinity equal to, is bounded, so this thing makes sense. S in S mod F of S. Okay. Prove that B of S is you can so you can, this is just the takes values. I mean, F plus G is just F of X. F plus G at X is equal to F of X plus G of X. You can add these things. You can multiply by a scalar. Okay. B is a Banach space. Okay. Okay. So this is bounded everywhere. Functions which bounded everywhere. There's no need. I mean, there's no measure structure or something. So that's also a Banach space. Then this is what is called L infinity is essentially bounded. So that's also a Banach space, and LP is also a Banach space. Okay, these are the three things. So whoever wants to do this, please contact me. And you can see this in any book or anywhere on the internet. Okay. Right? Okay. Okay. So what is next? Okay. Okay. So then there are more examples. More examples. So X is compact. Then all those C of X. I mean, compact mid. Let us take, you can say T2. I mean, it's enough that it's a compact Hausdorff space, but let us take metric space for our purposes. Then C of X is a Banach space with respect to this norm. Norm F infinity equal to, this is bounded, so F of X. So to prove this, if you have already proved B of S is a Banach space, then this is just a subspace of that, subspace of B of X, and you have to only prove it's closed. Okay, it's enough to prove it's closed. To prove it complete, it's enough to prove it's closed. I mean, all the triangle inequality, everything follows trivially, so there is nothing to verify. It follows from the triangle inequality for the modulus, for the complex numbers. Okay, so then the completeness is the only thing you have to verify, but then it follows from because it's closed inside the bounded thing. So if to prove it's complete, you need to go through something, but it's the same trick. But then C of X is contained in this B of X. Okay, so enough to prove that C of X is closed. So suppose F1 converges to F in this. That means it converges uniform, and uniform limit of continuous function is continuous function. If you don't know, that's the standard thing which follows from this. F of X minus F of Y is less than or equal to, you just write this inequality. Fun next. This is usually what is called the epsilon by 3 trick. Okay, this is the epsilon by 3 trick. So you want to prove continuity, so that you have to find a neighborhood around Y such that this thing is smaller than epsilon. Then you first choose a n such that this is where you are using the uniform convergence, so that F is uniformly near, I mean, this is uniform convergence, okay? Because the convergence in this norm infinity is uniform convergence. So since Fn converges to F uniformly, you can get a Fn, I mean, choose Fn such that mod Fn minus F is less than epsilon for all n greater than or equal to n naught. Okay, then you can have the n naught here. Okay. Then for with that n naught, first given epsilon. Okay, given epsilon, you choose n naught such that this happens. Then for that n naught, this is, I mean, here we are using the uniform convergence. This is less than epsilon, this is less than epsilon. Okay. Then you know that this is the, then use continuity to get a neighborhood around y such that this is less than epsilon. So that is really less, I mean, epsilon by 3, epsilon by 3, epsilon by 3, then that will be less than epsilon. Okay, this is the usual epsilon by 3 trick. I assume you have seen it in your analysis class earlier. So from that it follows that C of x is closed under all bounded functions, so it is complete. So someone has to prove that B of x, L infinity, all those things are complete. Okay, that is the next presentation. You can have it next week, either Wednesday or Friday or Saturday. Okay, not during the class. Okay, so someone please write to me. Okay, so these are all the examples. So you can consider more examples. For example, you can consider C1 of, let us consider only, I mean, a real number. You take an interval, C1 of AB equal to, this is just all functions f from AB to real line. I mean, this is over real, you can consider complex if you wish. I mean, that doesn't matter. Such that f is differentiable and continuous. Okay. Then you can define norm f. Norm
So do you mean the derivative is continuous?
Say it again.
So do you mean that the derivative is continuous?
Yeah, derivative is continuous. Yes. And yeah, f is differentiable and the f prime is continuous. Okay. And f prime is continuous. Then f1 infinity equal to norm of f infinity plus norm of f prime infinity. Okay. So this will follow from, I mean, you have to go through a theorem in analysis. If fn converges to f and fn prime converges to some g, then that f prime, I mean, fn converges to f uniformly. This is the thing. I mean, now my analysis course, I think we have seen, I'm not sure. Fn converges to f uniformly. This uniform convergence is important. And fn prime converges to g uniformly. Okay. Then f is differentiable. F is in C1 and f prime equal to g. Okay. You can prove this. So using this, you can prove that. I mean, you have to use this to prove that this is actually a.
So is that open AB?
What is open?
That should be closed AB, right? I mean, that's C prime space.
No, usually when we
No,
consider
because if you take
derivative,
open, then you can have unbounded functions like 1 by x on open 0, 1.
that's right. So
Maybe just make it closed AB and then talk about left hand derivatives and right hand derivatives.
it's just, I mean, it's integrable inside. I mean, it's differentiable inside AB. Okay, f prime is okay. You can say that. I mean, it's continuous. F is continuous in AB. I mean, it's continuous in the closed interval AB, and it's differentiable inside. Okay, that's what you consider. Okay, you can consider similarly. You can consider the complex domain, holomorphic functions on a domain which is continuous in the boundary and holomorphic inside, and that's also will be a Banach space with respect to corresponding norm. And
so what is the notation here? Norm f1 infinity, is it?
norm f1 infinity or something. You can use any notation just to include the one is the C1 and infinity is the infinity norm, just to say something. I mean, this is maybe confusing. We will not use these things, just to give more examples of Banach spaces. Okay?
So, and this is like norm f infinity plus norm f prime infinity.
Correct.
Okay.
Yes. Okay. Okay. So what else? Okay. So let us. So anyway, I haven't said anything about the sequence space of sequences. I mean, usually this is what is called LP. LP is all those sequences xn n equal to 1 to infinity, xn in C, LP of C or LP of R, whatever. Okay. Okay. LP can be from any set, it can take values in any Banach space, for example. Okay. Such that summation mod xn power p is less than infinity. Then you can in this comes. I mean, if you take the natural numbers with counting measure, then I mean it follows that this thing there is no need to prove it separately. Then you define norm xn. The sequence p equal to summation mod xn. This is usually called small LP spaces. Okay. Similarly, L infinity is all bounded sequences. Okay, and norm of xn infinity equal to supremum mod xn. Okay. Okay. So these are all LP spaces, and what else we have? Do we have any more examples? Okay.
What about the holomorphic functions?
Holomorphic function. I said it. I mean, you can take any open subset of C and consider the holomorphic functions. And I mean, there are theorems which will imply that if it converges uniformly, then that will be holomorphic again. So, okay.
Okay, so over C1 that is not completed, but what if so
You can take n derivatives and sum all those derivatives. That's also another thing, another way of doing it.
but then
So
what if
you
we
consider
consider
n variables and sum over all possible partial derivatives. You take that as a norm.
so but what do we consider the space of smooth function? Is that complete?
What is it?
Space,
General
space,
C infinity function?
yeah.
No, you can take the infinity norm itself. So if you take all smooth functions, then
No, yeah, that's not complete by Oyster's approximation theorem.
mm,
Okay, that's not complete. Never mind.
right. So what do you want to do now? That's right. No, that's not complete with respect to. I mean, C1 is also not complete with respect to the infinity norm.
Okay. I mean, yeah, okay.
Even it depends on which norm you are taking. Okay. Then see this norm, whatever I said, it is just the graph. What I mean is the following. You take the I said I took C1, okay, C1 of some interval or whatever. Then this is just you can consider this set, this F prime. Okay. So then this is maybe I will come to that when I use closed graph theorem or something. It will be clear. The norm I have defined is just the graph, the product. You take the product space and that is just the norm of the graph. Okay. You'll come to that later. Okay, so the next thing I want to prove is all norms are equivalent in finite dimension. Okay, though you seen this? Everybody has seen this. Then I may not do this.
We saw this in analysis too.
Yeah, and so in my class I proved, but not everyone is from my class, so I don't know. So this is a statement proposition. The proof is very easy, so let's just go through it. By the way, I assume everybody knows I'm not doing this Heine-Borel theorem that compact subsets of Rn is, compactness is equivalent to closed and boundedness in Rn or Cn or infinite dimensional space. Okay, I assume everyone knows this. If you don't know, you tell me now. Okay, I believe it's done in BSc everywhere. Okay, so I assume Heine-Borel theorem. Okay. What do we mean? What do we mean by norms are equivalent? So I have to say that first. So definition: X be any linear space. Okay, then X1 and X2 are two norms. On X, then we say norm X1 is equivalent to norm X2. Norm 1 is equivalent to norm 2 if there exists m, small m, in greater than 0, such that m times norm x1 is less than or equal to norm x2 is less than or equal to m times norm x1. Okay. This just means that if something converges in x1 in norm 1, then it converges in norm 2. something converges in norm 1, then because of this inequality, it will converge in norm 2. And similarly, if something converges in norm 2, it will converge in norm 1 because of the other inequality. Okay, so it just says that the convergence is same in these two norms. Okay, the topology is same, so closest are same. If you have only one of them, then we say this norm is dominated by the other one. If you have only one of this, then that will only imply that this is also equivalent to saying the identity function is continuous. Okay, is equivalent to saying identity function from x to x, okay, x going to x, is continuous with continuous inverse. Okay, is very important. Okay, continuous with continuous inverse. Okay, that's what this says. If you just think about it, that's what this. I haven't said what is continuous and all those things. Okay, but I'm just remarking. Okay, this is just a remark. We have to define what is. I assume you know already what is continuity in. So I will come to that. Okay, there is a linear operator between them, and so it's for linear operators. So that's what it means. What it means for. Let's prove the following proposition. All norms in finite dimensions. Okay, so how do we prove this? Okay, so we want to prove that all norms are equivalent. We prove that all norms are equivalent to one single norm, because you can check that this is an equivalence relation. Okay, it's easy to check it's an equivalence relation. Oops.
I did catch that. Could you try it again?
What is this? Okay. Proof. Okay. So check that this is a. I don't know. I touch somewhere and something happens. I don't understand. Relation. Okay, is an equivalence relation. Okay, which is easy. Okay. So because it's an equivalence relation, I just prove that all norms are equivalent to one single norm. Okay. So define. So let E1. This is a finite dimensional vector space. Let E1 up to En contained in X be a basis. Okay. Then you define the two norm as usual. Then define norm of alpha I summation alpha I EI. It's a basis, so every element can be expressed like this. This is equal to summation mod alpha I square whole power half. It's clear this is a norm, like we check it's a norm in Rn or Cn. So it's similar to that. Alpha is in scalars, either C or R, whatever. Okay. So I will prove that every norm is equivalent to this norm too. Okay. Let be any norm. X. Then we will prove that this norm is equivalent to this norm too. Okay. Okay. So how do we do that? For that, define T from Cn to X. Okay. Where this alpha 1 up to alpha n. Okay, that's how any vector in Cn looks like. Goes to summation alpha I EI. Okay. Okay. Then T is continuous. That is just clear. If some tuple converges to something, then it converges coordinate wise. That is clear. Cn with with respect to this norm 2. Okay. See, I mean, there is a norm 2. I mean, we have defined a norm 2. In Cn also there is a norm 2. So this is with respect to that norm 2. When we don't mention any norm in Cn or Rn, we consider this norm 2, okay, which is the usual norm. So with respect to this norm 2 and this with respect to this norm, okay, this norm, this is continuous. This is with respect to this norm. Okay. And this, I mean, this norm is preserved under this map. This T preserves this norm 2 here and this norm 2 here. Not this norm 2 here. Norm 2 is same in both the places. I mean, if the T takes, I mean, T.
So we are going to prove this.
We are going to prove what?
This result that T is continuous, right?
Yeah, I'm saying that is clear.
Okay.
Because if some alpha n up to alpha n converges in norm 2 in Cn, that means coordinate wise it converges. Coordinate wise converging each alpha I corresponding to the corresponding limit. Okay. Then the sum is scalar multiplication is continuous, scalar sum is continuous, because of that the corresponding thing is also continuous. Okay, that's all. Convergence in Cn implies coordinate wise convergence. That means all those alpha i's, the scalar component, that converges. So since the scalar component converges, the scalar multiplication, using continuity of the scalar multiplication and addition, it follows that summation of the corresponding thing, the corresponding T of that is also converges. Okay, so this is clear. Okay, check. Okay, so this map is continuous. Now, since this is continuous, another thing which we want to say is T of x equals 0, some x for x in Cn, implies x is 0. That is clear. T of x is 0 means T of some alpha 1 up to, or I will say alpha 1 up to alpha n. That will be more easy. T of alpha 1 up to alpha n equals 0 implies alpha 1 up to alpha n is equal to 0. Okay? That is clear because the basis is linearly independent. This is equal to alpha I ei. So this is equal to 0. Each alpha I is 0 because ei's are linearly independent. Its basis. Because of that, this is true. Okay. In particular, T of x not equal to 0 on the unit sphere. All those x in Cn such that norm x2 equal to 1. Okay, in the unit sphere. Okay, because it's only, I mean, it attains it's 0 only at 0. Because of that, in particular, it's not 0. And this is a you call it S1. Okay, and S1 is compact. Okay, so there exists T of x attains T attains at minimum. T attains at minimum and maximum. So there exists M So T of x is not equal to 0. So this is strictly greater than 0. I mean, Tx attains at minimum and maximum. So it is strictly, and this is, I mean, this is less than infinity and greater than 0. Okay, strictly greater than 0. Such that, so in this definition, M and M should be strictly greater than 0. Okay, strictly, I have written it. And M, of course, they are real numbers. Okay, so this is less than infinity and greater than 0. Okay, such that, because it's compact, such that M is less than or equal to T of x norm 2 okay, no, sorry, T of x. I mean, Tx is not equal to 0, so I mean, this is equivalent to saying Tx is norm is also not equal to 0, which is equivalent to saying, what is happening here? Which is equivalent to saying norm Tx is also not equal to 0. Okay? Because of that, there exists a M and M for all x in S1. Okay. But then for x general x in, for general, I mean, this implies for this means for alpha 1 up to alpha n in Cn, okay, this Tx is nothing but, we consider this. Okay. Now you call it alpha. Then you write it like this: norm of alpha 1 up to alpha n divided by norm alpha 2. Okay. Okay. This norm of this is equal to 1 because I am dividing it. This is in S1. Okay. I'm dividing it by the norm. It has a norm and I'm dividing it by the norm. So that has norm 1. Okay, 2 norm 1. So this implies for this yeah, this is intact. Okay. So then T of x is nothing but, then I mean, you just apply this to T of x. That just implies that this is norm of T of x. So that is equal to norm of alpha I ei, summation alpha I ei, okay, divided by alpha 2, I mean, which is same as if x equal to summation alpha I ei in x. Okay. Then this is now, this is same as norm x2. Okay, is less than or equal to m, less than or equal to m. Okay, and this implies m of norm x2 is less than or equal to norm x less than or equal to m of norm x2. I'm sorry, I have a little bit, I mean, made it a messy. It's very easy. You just have to use the fact that that map Tx norm Tx attains its maximum minimum in the circle, in the sphere. Okay. So it's clear to everyone.
Yes.
Okay. So that's all. That's the only thing being used. Okay. Okay. So if it is clear, let me go to, oh, it's going to be 5:50 already. I've taken a lot of time. Okay. Okay, I have 15 more minutes. So before that, I want to go to, so anyway, so this we have already done. So all norms are equal in finite dimension. Okay. So the next thing I want to do is, yeah. So there's a characterization for completeness. So which I will prove now. Okay. This is the following characterization. So this is the following proposition: X be a normed linear space X be a normed linear space. Okay. Then X is complete if and only if, okay, all xn, any sequence, you take any sequence containing in that, such that summation norm xn is finite, it converges. This just says that every absolutely convergent sequence, this is what absolutely convergent, okay? Absolutely convergent sequence. Every absolutely convergent sequence converges, which we know in real line, which you know for complex numbers. If something converges absolutely, then it converges. Here it says that if it is complete, then every absolutely convergent sequence converges. Similarly, I mean, you need completeness for that. Similarly, if every absolutely convergent sequence converges, then the space is complete. This is the statement of the proposition. Okay. So let us prove this way. Assume X is complete. Then we want to prove that every absolutely convergent sequence actually converges, has a limit. Okay. So it's complete. So we have to prove that something is Quotient sequence. We have to, it's complete. So every Quotient sequence converges there. Okay. So further then this way is easy. So suppose now we want to prove the following. Suppose xn is a sequence in X such that summation mod xn norm xn is in okay, is smaller than infinity. It's absolutely converges. Then we want to say that this series actually converges. Okay. So then we have to show that then we need to we want the following. We want to prove summation in k equal to 1 to n xn converges. Okay, that's what we want to prove. Okay, this has a limit. Oh, sorry. This is the sum. I forgot to say. I'm sorry. This is what I had in mind, but I wrote something. It's not the sequence converges. The series converges. I'm sorry about this. If and only if for all xn this happens such that then I forgot to write here. I'm sorry. Then summation xn.
Otherwise, a non-zero constant sequence is a counterexample.
Say it again.
Otherwise, a non-zero constant sequence is a counterexample.
Sure. Correct. Okay. Converges. I mean, there is too much of difference between series and sequence. Okay. This converges. The series converges. That's what I said when I was saying orally. That's what I was saying. Every absolutely convergent series converges. Okay. The series, not the sequence. Okay. So, okay. Okay, so then we want to prove that this series converges. Okay, that is, I mean, this series converges means that there is this, I mean, because it's a complete, since X is complete, it's enough to show it's a Quotient sequence. Okay, so enough to prove summation k equal to 1 to, so this should be k here. K equal to 1 to n is Quotient. That is summation k equal to n to m xn. This goes to 0 as mn goes to 0. Okay. Sorry, mn goes to infinity. Okay. But then summation k equal to n to m xn by triangle inequality, summation k equal to n to m norm xn. This goes to 0 since that's what it means. I mean, these are all just real number. Okay, that's what it means that summation norm xn is smaller than infinity. Okay. Okay. The tail convergence.
Statement, please.
Yeah.
Please show the statement of what you're proving.
Statement of the proposition.
Yes, sir.
Yeah, the statement of the proposition says that a norm linear space, you have a norm linear space is complete if and only if for any sequence xn, it is absolutely, the series is absolutely convergent, summation norm xn is convergent, then the series actually converges, which we know for real line, which is complete. So in the Banach space, this is equivalent to this criterion. This implies absolutely convergent, implies the convergence of the series is equivalent to the property of the completeness. Okay. So we have just proved the easy part that if it is complete, then absolute convergence implies the convergence. So this is just you just write the definition, direct definition. So, okay, is okay.
Yes, sir.
This way is also okay, I believe. Okay,
Yeah.
so let us prove the other way. Okay, so suppose every absolutely convergent series, okay, let us say series in X converges. Okay, then we want to prove that X is complete. Okay, so we want to prove X is complete. That's what we want to prove. So to prove that, so this X satisfies this property. Every absolutely convergent series converges in X. Okay. Then we want to prove that X is complete. So for that we have to take a quotient sequence. Okay. Let Xn contained in X be quotient. Okay. Then we have to find a limit. Okay. So this is the usual tail trick. So what do we do is the following. So since Xn is quotient, choose it should be 1 by 2 power n. Yeah. Choose n1 such that xn minus xn is less than 1 by 2 for all nm greater than n1. Okay. And choose n2 such that xn minus xn is less than 1 by 2 square for all nm greater than or equal to n1 and n2 and n2 is greater than n1. Okay, which is I mean, because it's a smaller number, it's a naturally can take it into greater than n1. Okay, like this. Choose nk such that xn minus xn is less than 1 by 2 power k for all n greater than nk, and n1 is it's in the other way, less than n2, less than n3. Okay, it's an increasing sequence. Okay. Okay. So what have we done? So then this thing implies whatever the construction. So I have just used the property of quotientness. Okay. By using quotientness, I have got n1, n2, nk. I mean, a subsequence of natural numbers, a subset of infinite subset of natural numbers, such that xn minus xn is greater than this. In particular, we have the following: xn1, xnk plus 1 minus xnk is less than or equal to 1 by 2 power k, I believe, for all 2 power k. That's all. Okay. This just follows with it. I mean, nk plus 1 is greater than nk, and for all anything greater than nk, this satisfies this, right? So this thing implies summation k equal to 1 to infinity. Okay, norm of xn k plus 1 minus xn k. Okay, is less than or equal to summation 1 by 2 power k is less than infinity, of course. Okay, so this is the usual trick. So this implies summation k equal to, by our criterion, our assumption is every absolutely convergent series converges. So this series converges. So xk plus 1 minus xk and k converges in x. So there exists a limit, converges, say, to x in x. Okay. Right? Okay. So this implies, but then what is this? This just means that k equal to 1 to n xk plus 1 minus x and k, which is just equal to xk plus 1 minus x1, right? This converges to x. This implies, sorry, this is not x. I have missed it. This is for a subsequence, okay? This is also here. This is also here. Okay. This is x n1. Okay. This implies x k n k plus 1 converges to x plus, this is just a constant. I mean, this is not a sequence. X n 1. Okay. So you have so this sequence xn is Cauchy and has a convergent subsequence. Okay. Then it's a usual epsilon by 2 trick. Okay. This implies xn is convergent. Okay. It's okay. So we have proved this implies x is complete. So we have proved that x is complete. Is it okay?
Yes.
Okay. So I have some 10 minutes more. Okay. So the reason for doing this criterion is to prove something. So see, we have already seen examples of Banach spaces. Now we want to construct more Banach spaces. From given Banach space, you want to construct more. So one way is to quotient space. Quotient space, or you can take direct sum. Then the direct sum, you have to define which norm you are defining. There are many ways of direct sum. Maybe you can take infinite direct sum. You can take uncountably infinite direct sum. All those things you can do. Then there is later we will consider tensor product. We will not consider tensor product of Banach spaces, but we may consider tensor product of Hilbert spaces. That's later. So the first thing to do is what is called a quotient space. Okay.
So how to define a norm of the infinite direct sum?
How to define?
How do you define a norm on infinite direct sum?
You have to take. You can't take all direct sum. You have to define so that the norm exists. It depends
Okay.
on which norm you want to define.
Okay.
You'll do it. Okay. It's see, L2 is just the infinite direct sum of complex numbers. So
That's
then you
true.
can. LP is just the infinite direct sum of complex numbers. But then you don't take sequences with all complex numbers. You impose a condition. Similarly, you impose a condition so that the norm is defined. Okay. It depends on which norm you are defining. Okay. So that it depends on that. Finite thing, there is no problem. You can define different norms using LP or something, LP or L infinity or something. For infinite thing, you have to impose a condition. It's not the whole all direct sum. I mean, it's not the direct product. Okay, it's a subset of the direct product. So that's all those things which are finite and there is satisfy a finiteness condition. Okay. Okay. Now we want to consider what is consider quotient space. So okay, let x naught contained in X is a subspace. Okay. Then we want to consider quotient space. Okay. Then X by X naught. Okay, this is a vector space. You know what is that? I hope all of you know this quotient space as vector spaces. Okay. And I mean, we say that this is all, I mean, X is equivalent to Y if X minus Y is in X naught. Okay. Then you consider the equivalence class. X by X naught is all those equivalence class. Okay. With respect to this equivalence class. Okay. I mean, if you go through any linear algebra course, then this X plus, you can write X plus Y. These things are consistent. Okay. I mean, it should be well defined and all those things. Okay. I mean, just the other way. I mean, it's this way. You add equivalence class, and this is them. You can take any element in this equivalence class, any element in the equivalence class, and add them, and they will uniquely define an equivalence class. So, I mean, it should be well defined. These are all you should verify using this equivalence relation. You can verify all these things. Okay. Similarly, alpha times it is this way. Okay. By definition, this is equal to this. You have to verify that this is well defined. You can take an equivalence class, you can take another equivalence class. Then the addition between these equivalence classes is defined. You take any element here, any element in one of the equivalence class, any element in the other equivalence class, then add them and take the equivalence class. It is well defined. It does not matter which element you take. Okay, you have to verify that it's well defined. These are all part of linear algebra course. Similarly, alpha times an equivalence class is also well defined. Okay, you can well define these things. But then to define a norm, you need something more. You will see why it is like why it is the case. So suppose we have non-linear space. Suppose X naught contained in X is closed. You can see that it's not defined otherwise. We will see example. Okay, we will observe that otherwise it's not well defined. It's not a norm. Then define norm of any equivalence class X equal to infimum of the norm, infimum of all the elements in the equivalence class. So any element in the equivalence class is going to look like this: infimum over x naught in X. Okay. Any element in the equivalence class is going to look like this. Any two things are equivalent if the difference is in x naught, so it is going to look like this. Okay, so the norm of this is a norm. This is the quotient norm. Okay, this is the original norm. This is infimum of this. Okay, so we need closeness. So then it's a norm. Then this is a norm on x by x naught. Okay, that's what we want to verify, and that should be clear. Because first, you can see that first, suppose how much time I have. I have only 3 minutes. So maybe I will leave it as an exercise. I don't want to give it as an assignment because it's very easy. Okay? So I need some more time to verify that it's actually, if X is a Banach space, then this is a closed subspace, then this is also closed. Anyway, the verification of norm is easy. I will the triangle inequality, all those things follows from the triangle inequality.
Sir, I have a question.
Say it again.
I have a question.
Yeah, please ask.
Okay, so we assume here that for any vector space X and any subspace of that, you can find a orthogonal like complement or complementary subspace of that, right? So let Y be a complementary subspace of X0 in X.
What you are saying is not true.
What?
How will you find an orthogonal subspace?
I didn't say orthogonal. I said complementary. So even orthogonal, complementary subspace.
What do you mean by complementary subspace?
Like a subspace Y such that X0 intersection Y is empty, is 0, and X0 plus Y is X. That's the linear algebra effect.
Yeah, but what will you do with that?
Okay, so is
It's
it
uniquely defined. I mean, how will you define
no,
it?
it's not uniquely defined. Just pick just extend any basis of X0 to a basis of X and then pick the even.
Uniquely defined.
Huh?
No, it's not uniquely defined.
It's not uniquely defined, but I'm saying there exists on or complementary subspace.
Yeah, but
Okay.
so it's not unique.
Yeah, it's not unique, but I already did one. So my point was that is X slash X0 homomorphic to the topology in the subspace topology of Y?
It depends. I don't think it's
Like
always.
I thought about this for some time, but I can't find a counter example. So can you give an example of that?
No, there are. You can see, given a norm, you have to find some complementary. It is like you have to find a projection, okay, from the biggest.
Otherwise, if that is the case, then we can define the norm in more simple way, that just consider the map psi from X to X
No,
cross
that
X
will be
plus
more,
X.
no, this is the simplest way. That will be more complicated to get a complementary space and define a unique norm and all those things. So when that space is not unique, how will you define it?
I mean, I all I need is a norm. I don't care. But if the topology is the same, then note that
No, no, no. You want to define the quotient space in a well-defined way. How will you define?
the quotient space is defined, all defined, right? But then we can find
Okay. So how will you define the norm?
we can find an isomorphism from X plus X0 to Y. The isomorphism will not be unique. I don't care.
What
But
do you
then
mean by the isomorphism? Has to be a normed isomorphism or just a linear isomorphism, just algebraic isomorphism?
just an algebraic isomorphism. And then you define the norm of two elements p bar and q bar in X plus X0 to be the norm of f of
But
X.
there may be two other things. How is the norm well defined?
But we found a map from X plus X0 to algebraic map from X plus X0 to Y.
Yeah, so there can be other subspace. No, you can define it through some other subspace.
Yeah,
Why is
I mean, all I need is a norm, right, that coincides with the topology.
no, but why all those things should coincide? I mean, it should be in a well-defined
I mean,
way.
why do I need that they should coincide? I don't care about that, right?
No, but then it will be dependent on the map, right?
Right.
Yeah, it will
The
be depend on
norm.
the matter, it will depend on the subspace, but we don't care about all those things, right?
Why we don't care? I mean,
I mean, are you using some uniqueness result anywhere till now?
are you using?
Did you use some uniqueness result so far in the norm?
Yeah, this is a well-defined way, no?
Okay.
I
this is
mean,
the-
first of all, I don't see why that complementary subspace exists. I mean, as a Banach space. Okay. I mean, you have to define it in a unique way. I mean, some well-defined way.
no. So complement also exists as a algebraically, and then you can just restrict the norm to that. Then you get a Banach space, right?
There will be some problem with that. I'm not sure what is the problem.
Okay.
So let me think about
So,
it.
is there a property that the norm of the quotient Banach space should satisfy? Is there some special thing that relates it to the norm of the original space?
Well, the quotient map should be continuous. That's one thing. Other than that, I don't see anything.
Okay.
Quotient map has to be continuous.
Oh.
And
Sir, in the definition of this norm, it should be infimum of x naught belonging to this subspace capital X naught, right?
yeah, of course. I missed it. Yeah, there is no otherwise. There is no point. Yeah.
Otherwise,
Sure.
it is 0.
Yeah, sure. It's x naught. That's why I use small x naught and x naught. Yeah, correct. That's a error, right? Anyway, let me think about it. We will discuss it more. So the point is, this is a norm which you can easily see. I mean, other properties are okay, but for this property, you need it to be close. Suppose this norm of this equals 0, then the infimum will be 0, and because it's closed subspace, then this just means that infimum of I mean, this is equal to 0, then that just means that, what does it mean? This just means that infimum of x naught in x naught such that norm of x plus x naught equal to 0. So there exists a sequence xn contained in x naught such that x plus x naught xn goes to 0, right? That's what it means by the infimum is 0. Okay, this goes to 0. And this implies xn converges to minus x. This implies x is in x naught. I mean, minus x is in x naught. Since it's a vector space, x is also in x naught. Okay. So this is equivalent to saying this is equal to 0. So this will not happen if that is not closed. For example, you take continuous functions and continuous function on a compact on 0, 1 or something. Then you consider polynomials.